Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a third video in a series on applications of Taylor series or Taylor series expansions. And in this video, we're going to focus on finding the error of an expansion using the alternating series estimation theorem. This is actually the ideal theorem to use. And this is a great example of how you can avoid using Taylor's inequality if your power series has an alternating form. So let's suppose that we are given sine of x and that we took the time to approximate sine of x so that it is x minus x cubed over 6. That's actually not too much of a time suck for us because we happen to know that the sine is just the summation n equals 0 to infinity of an alternating factor times x to the 2n plus 1 over 2n plus 1 factorial. And if you were to only add up the first two terms of this, so when n is equal to 0, you get negative 1 to the 0th, or 1, times x to the first over 1 factorial, and then minus, and this is because you're substituting in n equals 1, you get x cubed over 3 factorial, which is 6. So that's exactly what this is. So all we're doing here is a third degree Taylor polynomial expansion. And the question is, estimate the range of values for which that approximation is good to within 10 to the negative 8th. In other words, we want the error to be less than 10 to the negative 8th. Now, because our series that we're working with, the sine, is an alternating series, we don't have to go to Taylor's inequality theorem because we can replace it with the alternating series remainder test. So the alternating series test, the remainder for that is that the next term in line is an upper bound for the error. Then I've written it down here, and by the way, that's only true if the series is alternating and convergent. Well, we happen to know the sine is going to converge for all real numbers, so we don't have to really worry about that. Sorry, the series for the sine is going to converge for all real numbers. So what we're really asking is, if I look at the next term in line and I don't take the alternating factor, we get a bound like this. And of course that does clean up. That's the n plus first term. It cleans up to this. And we want that to be less than, this is what we want, 10 to the negative 8th. Now, solving this inequality may look pretty terrible, but remember, we know what n is, or do we actually? A lot of people will assume that n is 3 because it's the third degree Taylor polynomial that we're looking at it. However, what was n that forced that third degree? In other words, for what value of n would this exponent be 3? This is actually a very tricky question. While it's not so tricky if you just point at this and say, hey, what would I plug in for n to get an output of 3? Well, you would say n equals 1, and that's correct. However, a lot of people will say that actually the n value is 3 because of the way Taylor polynomials are defined. Sines and cosines skip over powers, so you have to be very careful. Be aware that to get t sub 3 there, you're actually only going to n equals 1. So I'm going to go back down to this. And again, we want to solve this inequality. We're going to let n equal 1. Now you may say to yourself or to your friend or to your instructor or to me if I'm your instructor that, wait a second, I thought we were supposed to look at the next term in line, not the current term that we're at, which is n equals 1. I thought we were supposed to go to n equals 2. but actually this formula right here is derived from looking at the next term in line. We are actually looking at n plus 1, where n is equal to 1. It's just that we've already kind of simplified the symbolic view of it, and now we're just going to plug in n equals 1 into that to find out what that will be. So when you let n equal 1, you get x to the 5th over 5 factorial must be less than 0 point, and then 1, 2, 3, 4, 5, 6, 7, and 8. Multiplying both sides by 5 factorial and taking the 5th root, you get down to this guy right here, which is approximately 0.065. I'm just going to round it to 3 decimal places, even though on my calculator I have like 9 or 10 decimal places showing. So what does this actually mean? It means that for our polynomial here to be accurate to the actual sine curve to within a value of 10 to the negative 8th, we can only consider x values that are at most 0.065 units away from the center. That is, you have some sine curve. That's our actual sine curve right there. I'll just kind of let it keep going. Okay. And we have a polynomial approximation, and the distance between our polynomial approximation and that sine curve is really small. It's basically less than 10 to the negative 8th is the distance between them. So they are pretty much on top of each other within this interval. However, the moment you get outside of this interval, that difference between the two functions grows to greater than 10 to the negative 8th. And you could check this using Desmos if you want to. Go ahead and graph the sine of x and then subtract from that x minus x cubed over 6. You'll have to do a lot of zooming in. I was going to show a video of this, but the reality is you have to zoom in so close that it almost defeats the purpose of the conversation. But it is true that this inequality does hold as long as x is less than 0.065 in magnitude. Honestly, it's actually the absolute value of x is less than 0.065. So that's a good example of the alternating series estimation theorem using that. The one warning I will give is to make certain that you know what your n values for your approximation are. So this 3 is actually associated with n equals 1. Yes, I get it that it's a third degree Taylor polynomial expansion. However, we only had to actually add up the 0th term and the first term to get to that third degree Taylor polynomial expansion. When we look at the alternating series estimation theorem and you look at b sub n plus 1, don't think n is 3. It's not. It's 1. So just be very, very, very aware of that, because that can lead to weirdnesses. Although, honestly, you just end up being more accurate, but still, it's important to realize that. It's only an issue when your power series skips over powers. Generally, most other series that don't skip over powers, you don't have to worry about. All right, that does it for this video. I hope to see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.